Today we're building this Liquid Text Morph effect in pure Java, no game engines, just Java2D. A living blob smoothly morphs into the word Java, then melts back. I'll show you every step, and you'll leave with a reusable class you can drop into any project. Create a new Java class named Liquid Text Morph. Let's start by importing everything we need for this project. Swing gives us all the window components, like the panel and frame, where our animation will actually appear. Next, AWT is the core 2D drawing library in Java. It gives us access to colors, strokes, gradients, and the powerful Graphics 2D class that makes smooth rendering possible. We also bring in Event. This one helps us handle real-time updates using a timer, so our animation runs continuously at about 60 frames per second. Then, we import from Font, which lets us convert text into vector outlines using FontRenderContext and GlyphVector. That's how we'll morph from a blob shape into readable text. Geom is next. This provides geometric tools like paths, shapes, and transformations, perfect for building and morphing our outlines. Finally, we import ArrayList and List to store hundreds of points that define our blob and text outlines. With these imports ready, we've got everything we need to start creating the Liquid Text Morph animation. Our animation class extends JPanel so we can draw graphics, and implements Action Listener to handle the timer updates for smooth animation. Now let's add the override method action performed for our timer. This method will run every time the timer ticks. It's where we'll tell the program to update and repaint the animation. Next, let's define the size of our animation window. W equals 800 and H equals 800. These constants set the width and height of our frame, making it a perfect square for the animation. Now we'll set up a few constants that control our animation. Word is the text our blob will morph into. Here it's set to Java. Points defines how many points make up our blob and text shapes. More points mean smoother motion. Base_r is the base radius of the blob. Speed controls how fast the morph animation runs. And FPS sets our frame rate, 60 frames per second for smooth performance. Now we'll create the key variables that drive our entire animation. First, we set up a timer. It runs every 1000 divided by FPS milliseconds, which means about 60 updates per second. Each time the timer ticks, it will trigger our action performed method to update and repaint the animation. Next, we create a variable t, which we'll use to keep track of time and movement in our morphing effect. Then we have two lists, blob PTS and text PTS. Each list holds hundreds of points, one for the blob's shape, and one for the text outline we'll morph into. By smoothly interpolating between these two sets of points, we'll create that liquid, organic motion. Finally, we declare a shape called text shape. This will store the vector outline of our word, so the program knows exactly what form the blob should take when it becomes text. With these variables ready, we now have the core foundation for our animation system. Now let's look at the heart of our resampling logic, the interpolation method. This function takes a list of points that form a shape, a list of their accumulated distances, and a target distance d. We start with int I equals 1, then loop through the list of accumulated distances. The loop keeps increasing I while the next stored distance is still smaller than our target d. In other words, we're moving forward along the path until we pass that target point. Once the loop stops, we know that the correct position lies between the points at index I1 and I. Those 2 points will help us calculate the exact spot for our interpolated position later. Now that we've found the general area of our target distance, we need to pinpoint exactly where along the path that point lies. We start by defining two indices, I0 and I1. I0 is the index just before our target distance, and I1 is the one just after. We use math.max and math.min here as a safety measure, to make sure our code never tries to access a point outside the list. If the value is near the start or end of the path, these checks keep everything inside valid bounds. Next, we retrieve the two distances that these indices represent, D0 and D1. D0 marks where the previous point is on the shape, and D1 marks the next one. Together, they give us the segment that contains our target position. Now comes the important part, we calculate a value called U. This U is basically the ratio of how far our target distance is between those 2 points. So if U is 0, we're right at P0, if it's 1, we're right at P1, and if it's something like 0.5, we're exactly halfway between them. We also include a safety check. If the difference between D1 and D0 is extremely small, we just set U to 0 to avoid division by a tiny number that could cause instability. Next, we pulled the actual points themselves, P0 and P1, from our polyline. Finally, we combine them using linear interpolation. That means we take the x-coordinate of P0 and move it toward the x of P1 based on how big U is, and we do the same for y. This gives us a brand new point 2D. Double that sits exactly where our target distance falls between the two. In simple terms, this code zooms in between two known points and calculates the precise spot that should exist between them. A critical step for creating smooth, evenly spaced points along our blob and text paths. Without this interpolation, the morphing would look jagged and uneven. Now let's build the heart of the liquid motion, the makeBlob method. This function generates the dynamic blob shape that constantly moves and ripples in our animation. We start by defining the method. makeBlob double time, int n, double baser. It takes three parameters, time, which controls the motion, n, the number of points that define the blob, and baser, the base radius of the shape. Inside the method, we create a new array list called PTS, size to hold endpoints. This list will store all the coordinates that form the outer edge of our blob. Next, we calculate the center of the screen. Cx and Psi are simply half of our window's width and height. That means the blob will always be drawn perfectly in the middle of the frame, no matter what size we choose. Now comes the loop. This is where the magic happens. We loop I from 0 up to n, so we can generate every point around the blob's circumference. Inside the loop, we first calculate the angle th. This converts our point index into an angle around a full circle, from 0 to 2 pi radians. It ensures all our points are evenly spaced around the blob. Then we calculate the radius r. This is where the blob gets its organic, liquid-like motion. We start with the base radius, baser, and then add a combination of sine waves that fluctuate over time. The formula is r equals baser, 1.0 plus 0.26 math.sine 3th plus time 1.35. Plus 0.13 math.sine 5th, times 0.9. Let's break that down. The first sine term, math.sine 3th plus time 1.35, creates three large waves around the blob. The second one, math.sine 5th, times 0.9, adds 5 smaller ripples that move in the opposite direction. Together, these waves interfere with each other, just like real fluid motion, giving our shape that smooth, wobbly, living look. The time variable continuously changes as the animation runs, so these waves appear to flow and shift naturally. After computing the radius, we use a bit of trigonometry to convert polar coordinates into Cartesian coordinates, that's just x and y positions on the screen. We multiply the radius r by math.cosine th and math.sine th. Then add the center coordinates cx and psi so that the blob stays centered on screen. Each new point is added into our PTS list with PTS.add new point 2D, double x, y. When the loop finishes, we have a full set of endpoints that define a complete, smooth blob outline. Finally, we return the list PTS. This list can be used to draw a shape, morph it into text, or animate it over time. So in simple terms, this method creates a circle made of points. But because each point's distance from the center is modulated by those sine waves, the shape looks alive. As time increases, the waves drift, and the blob keeps rippling endlessly. That's the secret behind its natural, liquid movement. Now we'll turn our list of points into an actual drawable shape on the screen. That's what this method, path_from_points, is designed to do. We start by creating a new general path object named GP. A general path in Java2D is basically a flexible container for connecting multiple lines or curves. It's perfect for building custom outlines like our blob. Then, we move the drawing cursor to the very first point in our list using gp.moveTo. That tells Java where the path should begin. Next, we loop through all the remaining points, from index 1 all the way to the end, and for each one, we draw a straight line using gp.lineTo. This connects every point in sequence, wrapping around the blob in the same order they were created. Once we've connected all the points, we call gp.closePath. That last line joins the final point back to the first one, sealing the shape into a closed loop. Without it, we just have an open spiral of lines. Finally, we return the completed path. This shape object can now be filled, stroked, or animated in our paint component method. In short, path_from_points takes all those individual coordinates we generated earlier and transforms them into one smooth, continuous outline. Ready for rendering as our living, breathing blob. Here we're creating a helper function called smoothStep. It first clamps the value of x between 0 and 1, keeping it within a safe range. Then we use the formula to create a smooth easing curve that starts slow, speeds up, and slows down again. We'll use it later to make our morphing animation feel fluid and natural instead of stiff or abrupt. Now we're going to convert any Java2D shape, like our text outline, into exactly and evenly spaced points. This is critical for smooth morphing. The blob and the text must have the same number of points, distributed uniformly along their perimeters. The text outline is full of Bezier curves. Animating directly on curves is tricky, so we flatten them into tiny straight segments. The flattening PathIterator walks the shape and approximates curves with lines. The second parameter, 0.75, is the flatness. Smaller values mean more, shorter segments and a closer fit to the curve. 0.75 is a good quality/performance balance. Next, we set up a few containers to hold our data while the shape is being processed. We create a list to store all the points that make up the outline once it's been flattened. Think of it as a collection of small connected dots that trace the edge of the text. Then, we prepare a small array to temporarily hold the coordinates that the PathIterator gives us as it walks along each segment of the shape. We also keep track of 4 variables, sx and psi to remember where each new subpath begins, and px and pi to remember the previous point as we move along the path. Now we reach the main loop that walks through every part of the shape. The loop runs while the PathIterator still has segments left to process. Each time through, it checks what kind of segment we're on. If the segment is a move to, that means the iterator is starting a brand new contour, like when it begins drawing the outer edge of a letter or a hole inside it. We record that position as both the starting point and the current point, so we know exactly where this section begins. If it's a line to, we're continuing along the same outline. We read the x and y coordinates, add that point into our list, and update the previous point reference so the next line connects smoothly. And if the segment is close, that contour is finished. We then manually add the starting point again to close the shape completely. That last step makes sure our path is a perfect closed loop, even if the original font shape expected the renderer to seal it automatically. Here eq will hold distances along the polyline at each point. We start at 0, then keep adding segment lengths. When we finish, L is the total perimeter length of this contour. The if L equals 0 guard avoids division by 0 in degenerate cases, like a shape that flattened to a single point. Now we produce exactly n evenly spaced samples along the closed path. For each desired sample index I, we compute a target arc length. Then we call interpolation method to find the precise point at that arc length, even if it lies between two raw vertices. This is what makes spacing uniform, no matter how curves were originally distributed. This uniform sampling is the secret to smooth morphs. If one shape had dense points in some places and sparse points in others, it would stretch and squish during the morph. By resampling both shapes uniformly to the same n, each point has a fair partner to interpolate to. A few tuning notes: lower the flattening value for crisper curves, raise n for smoother edges, and keep L equals 1 fallback to stay robust. If your letters have inner holes, make sure your source shape includes those subpaths. They'll be flattened and sampled in sequence. Now we'll prepare the text shape that our blob will morph into. This build text method converts a word into a precise vector outline, fits it to the center of the frame, and resamples it into evenly spaced points. First, we choose a bold display font type sans serif, style bold and size 360. Bold fonts give clean, chunky contours that morph beautifully. The numeric size here is large, so we keep plenty of detail before scaling. The FontRenderContext carries rendering hints for measuring glyphs accurately. Enabling anti-alias and fractional metrics helps produce smoother, more faithful outlines. Then we create the glyphs and get the outline path. GVObject takes our font and our word, and converts them into a vector-based glyph object. Next, shapeOutline extracts the actual outline of the text, all the curves, edges, and spacing between letters, and stores it as a single shape that we can draw or morph later. Here's the Fitbox Rectangle 2D target. It sits in the middle of the screen with safe margins on all sides. Width is about 72% of the frame and height about 34%, roomy enough for words like Java without clipping. Now we measure the raw outline bounds and compute scale factors. We calculate the x and y scales required to fit inside the target. Taking the minimum preserves the aspect ratio, no distortion, while guaranteeing the shape stays inside the box. Now let's set up our transformation. This creates a new transform object that we'll use to move and scale our text. Next, shifts the text so that it's positioned at the center of our target box. Next, scale applies a uniform scale to make the text perfectly fit inside the box, while keeping its proportions. Finally, translate moves the text so that its own center lines up exactly with the target center. Together, these 4 lines center and size our word perfectly inside the frame. Now apply the transform. Text shape is exactly where we want it, centered, scaled, and ready to render. Finally, we resample the outline. This produces uniformly spaced points around the text, matching the blob's cardinality so the morph is silky smooth. Now we'll set up our constructor Liquid Text Morph. Inside it, we define the panel size with setPreferredSize method. So our window matches the width and height we set earlier. Next, we set the background color using setBackground method. A dark blue tone that makes the animation pop. Then we call buildText method to prepare our text outline, and finally timerStart method to begin the animation loop. Now we're adding our drawing method. We use the @override annotation because we're customizing the paint component method from JPanel. Inside, the first line calls super.paint component. This clears the screen before each new frame is drawn. Next, we update our animation timing. Variable t, this keeps track of how long the animation has been running. Then we define a variable called cycle and set it to 3, that's the total length of one complete morph loop. Finally, tc calculates where we are inside that cycle by multiplying time with the speed and using the modulus operator. Now we generate the points for our animation frame. First, we call makeBlob, passing in the current time, the number of points, and the base radius. This gives us a fresh set of blob points that ripple and shift over time, keeping the movement alive and organic. Next, we check if our text outline has the same number of points as the blob. If it doesn't, we resample the text shape again using sample shape, so both shapes always stay perfectly synchronized. That's what makes the morph transition smooth. Every point from the blob matches directly with one from the text. Finally, we create 2 variables, u2text and u2blob. These will control the blending progress, one for morphing toward the text, and one for morphing back into the blob. Now we're defining the animation phases, how the blob morphs into text and then back again. The first if block checks if tc is less than 1. That means we're in the first second of the cycle, where the blob is transforming into the text. Here we set u2text using our smoothStep function, which eases the transition smoothly from 0 to 1. Next, if tc is between 1 and 1.5 seconds, we simply hold that shape, the text stays fully formed and still. Then, when tc is between 1.5 and 2.5 seconds, we reverse the process. This time we use u2blob, again with smoothStep, to blend the text back into a liquid blob. Finally, in the last phase, when tc is greater than 2.5, we hold the blob shape until the loop starts over. These time transitions create that seamless rhythm, blob to text, hold, back to blob, hold, repeating continuously. Next, we create a new list called interp to hold the points that represent our current frame, the result of blending between the blob and the text. Inside the loop, we go through every point index from 0 up to points. For each position, we grab 2 matching points, A from the blob, and B from the text outline. These 2 points represent the same relative position on each shape. Then we calculate new x and y coordinates by interpolating between them. We start by blending A and B using the morph factor u2text, which controls how far the blob has moved toward the text. That result is then blended again using u2blob, which gradually pulls the shape back toward the blob during the reverse phase. So each frame, Every point slides smoothly from the blob position to the text position and back again. By adding those new coordinates to the interp list, we build the exact shape that should be drawn for this moment in time. A perfect in-between form that makes the entire animation look fluid and continuous. Now that we've calculated all the interpolated points, we turn them into a drawable shape. We do that by calling path_from_points_interp, which connects every point in order and closes the loop, giving us a complete outline of the current frame of the morph. Next, we prepare a graphics context by converting G into a Graphics2D object. Finally, we enable anti-aliasing. This smooths out the edges of the shape, removing any jagged lines and making the animation look crisp and polished. Now let's paint the background for our animation. Here, we use a gradient paint to blend two shades of dark blue, one slightly lighter at the top, and one deeper at the bottom. This creates a subtle vertical gradient that gives the scene depth and makes the glowing blob stand out. The line G2, set paint defines that gradient, and G2, fill rect fills the entire window with it. So before we draw anything else, we've already set a smooth, cinematic background that fits perfectly with the liquid effect. Next, we'll add a soft glow outline around our shape to make it feel alive and luminous. We start by setting a custom stroke using basic stroke. Here, the width is 22f, and we use rounded caps and joins, that keeps every curve and corner smooth and natural, without any harsh edges. Then we choose a glowing color, a light cyan blue with some transparency, created using RGB values. That slight alpha value of 110 gives it a gentle, diffused glow rather than a solid line. Finally, we draw the path using draw method. This outlines our morphing form with a soft, liquid light, the first visual layer that gives the animation its glowing, fluid energy. Now we'll fill our shape with a soft color gradient to give it depth and motion. First, we get the bounding box of the shape using getBounds2D method. This tells us the exact area our blob occupies, its top, bottom, left, and right edges. Then we create a new gradient paint that blends two vibrant shades of blue. The top left of the shape starts with a light, icy blue, that's new color 120, 200, 255, and it smoothly fades into a deeper, richer blue toward the bottom right corner, new color 40, 120, 255. Finally, fill method paints the entire blob with that gradient. The result is a glowing, fluid surface that feels three-dimensional, almost like light is passing through liquid glass. Now we'll add a subtle highlight around the edge of the shape to make it pop. We set the color to a soft white with low opacity, new color 255, 255, 255, 85, that transparency keeps the shine gentle and not overpowering. Next, we use a thinner stroke, just 2.2f, to draw a fine outline around the entire shape. Finally, we call draw method to apply it. This adds a clean, glossy edge that catches the light, making the blob look more polished and giving it that professional, glowing finish. Inside action performed method call repaint method and then add main method for the class. Finally, we set up the main window for our animation. We wrap everything inside Swing utilities invoke later. This makes sure the program runs safely on the Swing event thread. which is the right way to start any GUI in Java. Inside, we create a new JFrame titled Liquid Text Morph. We tell it to close properly when the window is shut. Then set its content pane to a new instance of our Liquid Text Morph class, that's the panel containing all our animation logic. Next, we call pack to size the window automatically to match the panel, and set location relative to null to center it right on the screen. Finally, set visible true displays the window. And just like that, our morphing animation comes to life on screen. And that's it, your own Liquid Text Morph animation built completely in Java. If you enjoyed this project, don't forget to like, share, and subscribe for more creative coding effects. Thanks for watching, keep experimenting, and I'll see you in the next one.